we have is the route here. It's actually a router. We call something, it will do the route. Okay, and actually what is the route here? This is source code. Download source. Take a look. They have a Sun RPC, there's a Sun remote procedure call. Okay, and if you dig deeper, system dependence, you will see what are the things. 64-bit CPU, Spark CPU for the Sun OS. What else? IA64, very old architecture for 64-bit CPU. All the CPUs are here. Actually, it contains all the routes. You are from a specific platform, you will go through one of the directory and go to the real implementation and eventually route to the system call in the kernel. Okay? So that's why I said that I always say one lies. And the lies is you are calling system call and this is wrong. Okay? Later on I will give you some real code things. Okay? You look at the codes and say, oh, actually you are being cheated for 3 weeks already. Okay? So then, what else? The kernel source code. The kernel source code we won't touch deep today. Okay, next week we'll touch deeper. This is from the kernel.org. Okay, you can download it. And we have a very good system here. This free electrons guy, or what is it? Very good system. Okay, so you can take a look here. You can choose which kernel version. Okay, I choose the O series, the 2.4 series. When 2.4 series ends, it go to the 3.0 series and then go to the 4.0 series. Okay. Actually, in the middle is we have 2.6. Okay. The 2.6 is hard to explain to you. Okay, because you didn't go through that period. Okay. So this is the end of the 1.0 series. So it should be very mature. And why I choose this platform? Of course, I know many of it. And the code base compared to 2.6 is much smaller. Okay, 4 years before I asked them, Jimmy, to hack in the 2.6, they have a real disaster. Remember the completely fail scheduler? Yeah, completely fail. Yeah, very hard to hack and very hard to understand. Okay, so 2.4 is an optimal point for learning. Okay, and the technique that you use may, close to 80% can apply to the latest kernel. Some others are because of some of the multiprocessing thing. Okay, so this is the platform, and what is good about this platform? Let me choose one. You can go together with me. Let me choose the kernel directory. Yeah, I just choose it, and fork.c. Yeah, the fork implementation of the kernel. Okay. So what is the best thing about this? Of course, it has a kernel. All the kernels here, kernel codes here. You cannot find any syntax highlight. Okay. What I love is they have URL to point to the definition of a specific structure. Let's say this structure is called task struct. Okay. The task struct is the structure for holding every process's information. Let's click on it, and then it will tell you, hey, this task struct is defined in so many files. Okay, for you it is just like, oh, what are they? They look like encrypted things. Okay, I know where I find is here. Okay, and then boom, it gives you the structure definition here. Okay, so don't worry. 2 weeks later, it should be a holiday or something. I remember I have to go to UST for a talk. Then when we come back, it will dissect these all things. Okay, so this is not something difficult. Very interesting scheduler implementation. All right. So what I'm going to do in this talk is I already said that I will talk about what exactly is a kernel, and we will start to talk from the time we boot up the system. Okay. So when you boot up a system, actually for Intel CPU, particularly Intel CPU, we have a thing called, this is not on the notes. If you're interested, we will have so-called the ring protection system. Okay? So why it's called ring, it is something like this. Okay? Circle by circle illustration of the protection, and it's called ring. Okay, so I don't draw out the ring in a notes. I will tell you what exactly is different levels. Okay, we have different level of protection. Then this protection is actually starting with the thing that you want to boot up. Let's say you are not booting up an OS, okay? You can insert a floppy drive and ask, hey, load it in floppy drive. If floppy drive is not an OS, okay, it contains something else, then the protection system will stay at a particular level. If you put an OS, it will change the protection system level, and it will tell you what exactly it is. And the OS structure and design, okay, the OS structure and design is hard to say, okay. I just copied some of the materials from old books. We're talking about two implementation. One is monolithic, one is microkernel, okay. Then we will talk about how a system call is implemented. I said that it will go through a router called GNUC library. The GNUC library is a router, route the thing onto the kernel, so you are not touching the kernel automatically, okay. At last, I will talk about the kernel source tree. Okay, so you will be interested. Hey, when you download the source code, okay, how many files are there? Let's try. Okay, so I don't know whether you know how to do a. Do you know how to count how many files in a directory? No one knows? Oh, sorry, no one knows. This is a rough estimation including the directory names and as well as a current directory, approximately that many number of files. Okay, so we can do a count like this. So many files. So how can you traverse the entire tree? I will tell you. Okay, so then after that we know the kernel structure. Then we will try to compile kernel, and by compiling kernel, I will give you a warning. This is the moment that if your machine is not have 100% of the battery, now charge, okay, up to 100, okay, yeah, here, oh, okay, I removed it for you, okay, yeah, charge it out, okay. When you boot up a virtual machine and try to install the thing, it was just a huge power consumption. Even my MacBook Pro dropped below 50%, okay, after finish all the tests. Yeah, the table can move. Yeah, you can move the table. Yeah, the table can be moved. Yeah. 有冇人有拖板啊？喂，有冇人帶拖板 ？Yeah. Yeah. Remember, this is the time for you to charge your battery. Yeah. All right. Yeah, this is not a joke. Okay. Last year, half of the students failed to install it completely because running out of battery. Okay. Running out of battery. Oh, no power. You have to stop. Okay. Yeah. Okay. I give you this. Okay. I give you this. Yeah. I don't need so many power. All right. Yeah. Interesting class. Yeah. Every people just like that. Yeah. Just no one 冇人有拖板啊。你都冇話要帶拖板係咯 ？Helen 有講喎。有咩？有。Helen has a reply talking about battery. 有講但係冇講。Yeah， 冇啊。有冇人有 ？Any people know society people? Society rooms should have many. 冇人啊！有阿姨嗰啲近啲啊。係裝夠樓。啊，院會 sorry， 院會夠樓。All right. Let's go. So protection, what is the protection I'm talking about? Okay, so actually CPU has at least two, okay, mode. One is privilege mode, one is non-privilege mode. At least two, okay. So that's why I said there's a ring system. The ring system is actually give you different levels of privilege. At least you will sense two privilege. One layer is for ordinary process. Okay, so you have a process, you go to the CPU and the CPU run at one particular mode, and that particular mode actually is very kind of funny. Okay, I list out the questions here. Okay, so what I just said is the process go to the CPU. Interesting, right? What is the meaning of process go to CPU? Does it mean that CPU know what the code you're running? Actually, no, right? They're just instructions. Okay, so that's why there is a mode change here. You can switch from one protection mode to another protection mode, and this switch is a privileged instruction. Okay, so that's why CPU don't know. it's only the kernel inside the core and inside privilege mode can switch it. Okay, and here who tell which code CPU should run. Okay, now you get the idea. In what happened? Shit, shoot. Okay. Every time it's like this. Okay, yeah, you don't know. Okay, when I was using ERB building lecture for any core, okay, I would drain his battery. Okay. You can ask some people from last year. They will say that yeah, every time most has to change battery. Yes, every time, no matter which room it's ERB. No matter I'm teaching OS or ENGG 110. Yeah, this building is always against me. Yeah, good. Battery is back. Okay, so the CPU mode. Now you get an idea. Hey, there is 2 modes. Okay, so I was asking another questions. Yep, we know there are mode, but who tell the CPU which code to run? Okay, you get an idea. I talk about it in a normal class that there is a kernel, and the kernel has a scheduler, and actually the scheduler will put codes into the CPU. And this will make it very, very explicit when we go to the scheduler class. I will talk about what exactly are the assembly code, okay, to switch it, okay. Now, what's next? Next is, in the lecture, normal lecture, you already get the idea, hey, kernel has ability to take someone else away from it, right? And what exactly is the control? Yeah, it seems that it's strange, right? When you write your program, you don't have an instruction put in your program said that now this is the time that I can run away from the CPU. No, there's no such control in your program, but the kernel has it. Okay, so I can give you a hint. You can follow the timer. The timer, let's say that every 1 millisecond is good. 1 millisecond, then the clock will raise the interrupt. Okay, yesterday I talked about interrupt. Raise the interrupt, and when the interrupt routines run, this is the time that the kernel can step in to choose whether the original process should go away or not. Okay, so there's a call to call the scheduler to choose, hey, whether you should stay or out. Okay, and here comes the different flavor why we choose 2.4. 2.4 is very bad in processing this area. We call it a multi-CPU or multi-processing system. Okay, 2.4 series is very bad. Okay, many people complain about this is a capability in handling multi-CPU. And in 2.3, no, sorry, 2.6. I mean 2.6 and 3.0 and all the way up to 4.0, it has a very significant improvement here, and that's why when you take a look at the 2 version of the codes, even on the same function, it's changed a lot. Okay, so for us, we're beginner, so that's why I will choose 2.4 in order to avoid this problem first, and then I will keep mentioning that, oh, okay, there is a code, and this code, when we go to real stuff, it will change. Okay, then memory, right? Memory sucks, okay, really sucks, okay. It's very difficult to explain to you, okay. So I will only say that this is a placeholder. Every time I say this placeholder for you to host what? Host code, your global variable, local variable, malloc, okay. And in the kernel, they look at a different way, okay. They are boxes, okay. We call it memory page, okay. So later on, you will see some variable names called page, okay. It's actually a 4K block. Okay, just give you some idea that kernel handling different things differently. Okay, and yeah, these questions. Okay, so this questions is about the previous thing that I talked about in the regular lecture. Whether it's good to process a piece of memory everywhere in the system, like let's say I have a kernel data structure, only limit to the kernel space. Okay, so actually this protection ring of the CPU switching from privileged mode to unprivileged mode is actually also talk about this area. Whether you can touch system memory for kernel, or you can only touch with users. Okay, and Other codes I will skip, okay, because you already get some idea. Hey, actually there are separations of two worlds, okay, and the separations or their illustration, we can use this simple graph to talk about it. The blue blocks, the real mode, okay, is the mode that when you first boot up the machines. When you first boot up the machine, I don't know whether you have heard about this, okay. This motto, this is not a motto, okay, it's Bill Gates says. Bill Gates, okay, Bill Gates says, K memory. Yeah. Is it this? No. All right. Yep. Bill Gates, no, 64K, 600K. No, this is not. Oh, yeah. It says here. This is not the crow. The crow is very sexy, okay? He says that 64K ought to be enough for everybody. Yeah, this is what he exactly says, okay? And why he keep on mentioning this as 640KB, okay? Do you believe that you can survive with this amount of memory? Yeah. But at the time that I use computer, games really take this amount of memory. Yeah, many games are doing that. Okay, when the games trying to access further things, we have to type some command to enable it. Okay, and why is that? Why is that? Part of the reason is not the complete reasons. Part of the reason is because of this kind of a different user mode, protected mode, or real mode. Okay, when a computer first start up, okay, it is only have a very limited view on the machines. It access why it's called view. It access the system memory from address 0. Okay, and nowadays, let's say in a Linux kernel, okay, it can only access up to 1 GB. How many bits here? If I call it 1 GB, how many bits I need to store 1 GB? Do you know what is 1 GB? 2 to the power? Huh? No. 1. How come there are 4 there? Of how many? 10 is K. 20 meg. 30 is GB. Okay? So inside the protected mode, okay, the protected mode of Linux, okay, they actually put a jail on a system that it can only access up to 30 bits for that particular code running inside the kernel. Okay? And in the real mode, it's even more horrible. Very, very limited thing. Let me give you an example. There is a boot code, okay, the boot code in every operating system. I don't know whether how many of you have used DOS? Yes, DOS. Never use it? Try once, okay? Download it, your computer won't explode. DOS, boot this. You put this, okay? Yeah, try to download it. And remember, if you're afraid of what will happen, remove all your hard drive first. If this is your floppy and your laptop, okay, without a floppy, then you can apply that, okay? If you are using a computer with floppy, you can even put it in a floppy. Now, if you don't have a floppy, okay, they have ways to put it in a USB, okay? Why I want you to get it, okay? You get it and take a look. What is the size of the image? 1.4 meg. 1.4, okay, of the megabyte. Then you can boot up a DOS system, okay? And DOS system already an operating system, okay? And you can try that. If you're afraid of it, okay, and you have a real desktop computer, remove all your hard disk cable first, okay? Because you're afraid, right? Remove them all and try to boot it up and see what it is, okay? And actually, it's the same environment that I showed in the DOS box. Okay, Jimmy is very happy now. Yeah. Try it. Yeah. Try that interesting thing. Okay, and the example is not stop, right? I just talked about the 1.4 meg. It contains files. Okay, it contains file system FAT12 file system inside. And this is not the code that for you to boot up the system. To boot up the system is 512 bytes. Yeah, that's small amount. That small amount of thing put into the memory and run, it become the initial code for the operating system. And the real mode is to operate in a very limited amount of memory, because it's access some real things. Okay, originally the real thing is not for operating system. Okay, it's for the boot code. Okay, and after some change inside the boot code, one of the instruction is to tell the CPU, hey, now I am taking in charge of this computer. Please switch to protected mode. Now inside protected mode, we enlarging the accessible memory amount from a very, very small range to 2 to the power 30 for that particular OS code. So that's why the OS code don't care about what is the operating system you are, whether 32-bit, 64-bit. At least you have this kind of amount of memory. And how about the old system? No problem. Okay, old system we can extend the memory address by using some other ways. Okay, we call it virtual memory. But when the system just start up, it won't take up all the 1 GB. Okay, it just reserves the 30 bits for it to operate. Okay, and inside here is just by changing a CPU register. Okay, just an instruction, change the register, and then it will become protected mode. And inside the protected mode, we have so many things. Exceptionally highlight here is what we call privileged instructions. So what are they? Including halt the computer, halt the CPU, shut it down. Okay, including clear all the memory cache. Okay, including some of the things that you never heard of. I can give you a list. Okay, invalidate the cache. Invalidate. Oh, what's this TLB? Okay, TLB we call it translation look aside buffer. Is for virtual memory. Low system register. The system register, one of the system register is for switching from one process to another. When it get update, it will suddenly switch to another process. Change the operations of the I/O operations. Let's say to change the how can I describe it in the lecture? Interrupt routine. Okay, I describe it in the lecture. Usually I will call it IRQ routine. Okay, interrupt routine. Okay, halt the processor. Okay, you can Jimmy, is that the Tsinghua University? They are halting processor in our context, right? Yeah, I remember it's something like this. Okay, we are working on a supercomputer competition. What is the year? 2013, right? Yeah, 2013. Okay, we are going to a competition. The competition sucks. Okay, how sucks it is? The supercomputer center, the fields can jump. Yeah, while we're doing the competition, okay, you know, supercomputer have many fans, so very noisy, okay? So, yeah, very bad, yeah. When we are talking, and then suddenly we find that the entire corridor have no sound at all. So they, no sound? all the computers shut down, okay? In Shanghai Jiao Tong University, sucks, okay? And well, one of our criteria is to limit the power consumption. Okay, Tsinghua University doing one very horrible things. They know how to write those privileged core. They have a multiple core, let's say 16 core. They shut down half of it. No, it's China. The China Tsinghua University. Okay, well, very not cool. Okay, but I think that they really know very very deep things. Okay, and they know how to halt a particular processor to save the power consumption. Okay, for us we don't know. Okay, we just can I keep the loop smaller? Can I save some of the consumption, so and so forth? Yeah, our ranking is not good. Okay, but they know. Okay, there are many privileged core that you can try, but only in protected mode. And then when we finish executing those things, let's say we have a time that the clock say that, okay, it is time to stop for a while. I give you a timer interrupt. Then you switch into this area. We use privileged instruction to load different process in, swap a process out, swap process in using privileged instruction. Then after this, we will use the last privileged instruction to resume the user mode. Okay, so what is that last instruction? We call interrupt return. IRET, interrupt return, and then it will go back. So this kind of call is also considered as one of privileged instructions. Okay, so you cannot call it in user mode. So the user mode code is very lonely. You cannot change anything in the CPU. You can only run a code or issue one call. It is a legacy call, but it is easier for you to understand. You raise the instruction, and the instruction is called interrupt. So you artificially generate interrupt. Yesterday we talked about interrupt, right? And the interrupt has a set of numbers. I said that, oh, let's say the interrupt 1 is the timer, interrupt 2 is the keyboard, so on and so forth. And we have the interrupt has a decimal number 80. And it is a system call interrupt. So when you issue it, the computer suddenly will change into protected mode. Okay, you can issue by yourself. I try in a time that I have to write assembly. Okay, I call in Windows it's interrupt 20 or something like that. I can't remember. And then suddenly it will jump into the system call body. Okay, I don't know how to change it because it is code inside the kernel. But I set up the things, the parameters, and then say that okay, interrupt ATH, and then boom, jump into this area. Okay, then after this it's just some privilege call. Let's say that you are trying to schedule another process, then come back. Okay, so this cycle is keep on running until you shut down your computer. It won't come back to the real mode because real mode is the boot time. Okay, so any question you want to ask or some rumors you have heard before you hear someone talking about this. Yeah, maybe you have heard some rumors from previous school, some of your friends, okay, so on and so forth. And my job is to clear those poisons, okay, remove those poisons. Okay, no? Not cool, huh? Because you cannot see any code. Okay, so operating system design, wow, nowadays is usually a mix. Okay, there is some story. Okay, the story about this. The story is Linus, this guy versus Andrew Tannenbaum. So what this you know this guy, right? How many of you don't know this guy? The Linux kernel author. Okay, so what is Tannenbaum? The Tannenbaum is you already find this guy in our course homepage. Okay, not this. Tannenbaum. Tannenbaum, where are you? Here. Yeah, no one knows, but no one buys this book. Okay, Andrew Tannenbaum is this guy. Okay, they crossfire. Okay, how they crossfire? Okay, it's very interesting debates that happen in a mailing list. Okay, the mailing list start with Linus said that okay, we have a monolithic implementation of an OS. So what is monolithic? Okay, monolithic means that this is the illustration. Don't care about this. This is the illustration. Monolithic means that you have an application, you have your process run in the user mode, and then you issue a system call. That is the interrupt call. You jump into the protected mode, and the protected mode contains many codes. The VFS, the virtual file system, IPC, inter-process communication, file system, scheduler, virtual machines, device driver, dispatcher. I don't know what it is. I mean, I never find a word in dispatcher in the Linux kernel. Okay, as well as the driver touch the hardware all in one. Okay, it's just a compilation, compile all things and put it into one executable. Okay, we call it monolithic kernel. Okay, Linux was a monolithic kernel. And other guys, Andrew Tannenbaum say that no, this won't be the trend. He thinks that the trend should be microkernel. So what is microkernel? Microkernel, you have your application running, and a system call, you can still issue a system call, but alongside with the application, you can find other things. You can find some process, a real process. Some processes running alongside. Each process has its own task. Let's say one process is handling a file system, one process is handling or a file system. Okay, some handling the keyboard, some handling the USB. They become a process of the same privilege as you. Of course, this is running at root. Okay, the administrator. Okay, and a system call when it go when here the kernel is doing minimal, is treated as a drive as a router, route your call to a specific server and wait for the server to return the results and give you back. What is the good? What is the bad? Here, extremely hard to debug. Think about it. I don't know how many codes you have right. Okay, my records is of course more than 10,000 lines of code. Okay, think about it, and everything we cannot put it aside. You have to run as a whole program. It's a very horrible thing. Okay, and here you are just dissecting the code, not just the code, but also the binaries. When you compile it, it becomes different executable to shield the errors. Okay, so Andrew Tenable think that this is the future, and he even write a new new operating system. I don't know whether you know it. Minix. Yeah. Why is .com.hk? No, it's not Minix. Andrew Tenable. And what? He's removed from Google. 10 or TN, okay. 10. What happened? Copy and paste. And Tenable, okay. Minix. See, Minix is having a hard life, okay. It cannot even exist in Google, okay. I just type Minix, but give me minix.com.hk. Okay, you believe in it, okay? Minix is not minimize Linux, okay? It's not minimize Unix, but an implementation of Unix-like operating system based on microkernel. You never heard of it, so you know this debate who is the winner. Yeah, the winner is not microkernel. The winner is monolithic kernel. But monolithic kernel has its own problem, okay? The problem is very hard to debug, really hard, very hard to debug. But let's say the VFS, the virtual file system, has a bug, segmentation fault. What will happen? Kernel segmentation fault. And what is the game that ends when you have a kernel segmentation fault? Blue screen of death. So Windows has many segmentation fault in here. And of course, Windows is a monolithic implementation. Okay? So how can you survive in this kind of implementation? So the Linux implementation knows that we cannot follow this model for a very long time. We have to migrate to this model. Okay, so we are standing in the middle of it. We have many kernel drivers, subsystem become a .o, the object code. And when the kernel lists it, it will link this .o, the object code, back into the mainstream here. And when you don't list it, you can deallocate it, okay, as if a subsystem. But no, it's not a subsystem. It will be loaded inside this tree. Okay, so it's still a part of a monolithic implementation. Okay, so this is the difference between different implementation. And do you know that there are still existing microkernel operating system? You never heard of it, right? You know, maybe this is the first time that you've heard of microkernel. Yeah, there is a system still using microkernel, and you are using it every day. This guy. This guy is a microkernel. So what would you expect? Yeah, you're telling you made lies, a lot of lies, okay? Yeah, here you say that it's bad implementation, but we are using it every day in Linux. And this is a Minix. Oh, Minix dies already, and it become a Darwin operating system, and we're using it every day. Now, what is the good and the bad? The pros and cons is the monolithic is very fast, extremely fast. What is this very fast? Compared to here, you need a router to route your call to a specific server, and then let it run for some time and route back your results. Extremely slow. Now here, no router, give me the call results immediately and return it back to the application. So actually, under this system, Mac OS is very slow actually. So Mac OS has the potential to become faster. Okay, and Linux is actually I cannot explain, okay, because Linux has a very strange community. Do you know what is a community? There, you can become a kernel implementation developer. You just join their Git repository and file pull requests, and then you can call yourself Linux developer. Now, what is the problem? There are a bunch of people get paid for it. Red Hat, Microsoft, HP, IBM, they have employees injecting codes into Linux, and their goal, what is their goal? Of course, to give their own product the best performance. Okay, so Linux is kind of migrating from a desktop environment. There's a lot of efforts that people want to make Linux to be a desktop environment. I already jumped ship. Okay, for a few years before, when is that? After teaching Jimmy, okay, yeah, that year, it's particularly that year, okay, I found that the desktop environment of Linux sucks. Every time I run a virtual machine, it's crash. Okay, so you expect that I crash every day. Actually, when I want to open a DOC document in a virtual machine, boom, reboot. I want to do something in Windows, boom, reboot. Okay, then I forget about it. Okay, because no one care. All people care about performance now. How to make it better, how to run a virtual machine on top of it better, how to make it become optimized for, let's say, Amazon Web Service. Okay, people migrating to that area. Monolithic is like this. How about microkernel? Microkernel is the biggest player is this guy. Okay, they have code source, but they are still contributing using another stream. Okay, hey, go ahead. I already talked about all the things here. Okay, Linux, Unix, Windows are all monolithic, and microkernel, they are, yeah. Take a look at what this guy says. It's just stupid. He said it's just stupid. So as long as he is still alive, he is still in charge. You know, every pull request that's submit to the Linux mainstream, okay, Linus will take a look. Okay, so that's why you will see something. I put it up in Facebook. You never see it. I don't know because no one like it. When you like it, then I know. Where is it? Should be about 1.1. Right? Where's 1.1? Well, seems to be a long story before. Hey, what is it? Oh, where are you? Warm up. Oh, hey, here. So he is cursing. So they are still using a mailing list. Okay, whenever people fire a pull request, okay, it will take a look. Okay, and usually the pull requests are kind of side with this document, side with the driver. Okay, someone submit a bad driver implementation, and this guy cursing, keep cursing this guy. Oh, why you write it in C? Okay, in that way. Okay, please learn C. Okay, yeah. And he is still in charge, okay? Even though it's already 25 years, close 25 years after the birth of Linux, okay? He is still in charge of this. Every people submit the code, he will read, okay? So I wish I would have that kind of amount of time, okay? I don't know why he had that amount of time, okay? So this is the microkernel. The microkernel implementation still is a mystery because we cannot see the Darwin code, but I said that there's an open source alternative, the BSD. FreeBSD, NetBSD, they are all open and they are following the microkernel implementation. And if you want to know the history, I found a very good article, okay? You know, I don't know whether you get the sense, okay? You know that China IT development, particularly very hardcore technology, I guess China is better than Hong Kong and Taiwan multiplied. Okay? Don't think that China knows nothing. They are very, very hardcore, especially those very low-level things. They have a very good team of people in, let's say, in Alibaba. Okay, they will change kernel code. They will write a very low-level file system, let's say, to satisfy the Hadoop system. Okay, they are doing this kind of thing. So their article is actually full of juicy stuff. Okay, you can take a look at their article. You will find that when they mention something, actually you never heard of it. Okay, so I really enjoy reading this kind of thing. Okay, I even order a magazine. Okay, but the magazine dies already. Yeah, order a magazine that's called 普通话不要忘了 okay 程序員啊 yeah, there is a there is a very good 唔係 monkey Ching. So, this one. No. It's a programmer. The link is should be. They are still having a online. This one. Online archive for all the magazine. When I first flip it, I think I only know half of it. Okay, and they keep publishing. I find that wow, they're really very deep. Okay, so I just claim, I think this is a true claim. The capability of Hong Kong times the capability of Taiwan is still smaller than the capability of IT people in China. Prime times, not plus. Okay, Hong Kong sucks. Now Taiwan is better. China, we cannot beat that. Okay, I mean, because they have their own requirement, right? They won't use Linux. Okay, they think that Linux is from the United States. They may inject something in there. So ask an engineer to tell me whether they are injected code to steal our secret. That guy, okay, will learn a lot, right? Let's say now we know that we want to modify that so that we can steal other people's things. Then that guy will learn a lot again. Okay, so that's why you think that this is just a positive feedback loop. Okay, they keep rejecting other things. They will keep their own things better and more evil. Yeah, so that's why they can steal other things. They can even hijack the code in Xcode and give you a Xcode that can build things with malicious code. Okay, so their IT level is very high. I already know it. Okay, so let's go through what happened in a monolithic OS. Okay, so for monolithic OS, I give you an example which is easy to understand. This is what we call DOS. Okay, so if you don't know what is DOS, you can go to download DOS box and execute once, then you will get the sense. So what is the DOS? DOS will have a user. This is you. You interact with their just like shell things. We call it command line processor. Okay. Then immediately it will go into every commands will go into the DOS kernel, and the kernel is very small. You just need a floppy drive, and then you can run a DOS. Okay. Then the DOS kernel will directly touch the operating system, hardware, and the BIOS. Okay. How many don't know what is BIOS? Good. Everyone know what is BIOS, right? No? How can I explain to you? Yeah, we put your machine, then you will know what is BIOS. That thing, the splash screens, okay, is actually a part of the BIOS. Okay. Later on we will show it. Don't worry. Yeah, it's now become a computer assembly course. Yeah. Yeah, we talk about those BIOS. Okay. And you are the user. You're the only user. So in a non-threaded, now hear me. Non-threaded or non-multi-processing operating system, only one guy, one process control OS. What exactly is a monolithic OS is very easy to understand now. I type something, and before I can type something, already we have memory management unit to dissect the memory into a chunk. Okay, in English we call zone, Z-O-N-E. We have the different zone of memory. It is being put up and already dissected now. We have another file system. DOS subs only support one file system. Okay, the FAT series, and I/O, the controlling the driver. And then you issue a command. You are the user. You type, and then you issue a command, and that command will call the system call and go through the kernel. The kernel either go to one of the branch here and eventually touch the hardware to show you the results, or get it from the hard disk, so on and so forth. Now, what is the threaded implementation? Threaded implementation is sexy, okay? Really sexy. You can allow two processes at the same time calling system call, okay? Remember, kernel is not a process. Kernel is always a piece of code with memory living in the system. So when you call it in parallel, you are just, let's say the core CPU core A is running your system call, CPU core B running your own system call, and they all both go through the INT-ATH, that's instruction to switch into this area. Okay, so this switching supported by both core, and you are just switching the ring protection system of that particular core. Understand? Very important thing. Okay, you are just changing that core, not the entire system. I don't know how many cores, how many CPU you have. You're controlling that core. So that's why you can go into different path inside the kernel now. You are going to touch the area here. Okay, so you are supplying arguments, whatever things you want, but remember what is arguments or what is the code that you're running. Actually, you need the support from local variables, right? You run a code. Usually you process local variables, right? I don't talk about operating system, how to process malloc and global variable. I just talk about local variable. Okay, you need it. Then how the multi-threaded kernel gives you local variables. For the DOS, it's easy, right? For the DOS, this is the entire memory. Yeah, feel free to take it. Okay, and in the kernel, Linux kernel here, you have to support separation. Okay, and the separation we call it kernel stack, and it's its own task structure together with the kernel stack. Okay, and the kernel stack is close to 8K to store your input. Okay, and this input will correspond to your task structure, and the task structure interact your local variables. Now let's say you need to run the program using malloc now. Okay, your program, I mean the system call, not a program, the system call need to malloc, need to allocate memory inside the kernel. So in the kernel, it's its own version of malloc. We call it kmalloc. Yeah, kernel version malloc. Yeah, next time I will allow you to run it. Okay, very easy to write, just the same argument list for malloc. Okay, then you can allocate memory inside the kernel, and we don't call it malloc. We don't call it dynamically allocated memory. We call it slab allocator. Okay, just a name. Okay, this is just a name. So we have now what we have. We have local. We have our own structure to controlling what we should do. That is your PID, your memory allocation information. All here we have malloc now. Where is a global variable? The global variable for a kernel is very horrible. Okay, you will have a chance next week. When you want a global variable in a kernel, just write it in any one of the C code, then it belongs to you. Okay, and that means what? That means you can change other. Let's say I want to change the memory management unit there. I know there is a global variable called stupid mode. Let's say. Okay, and you can modify the stupid mode variable. Okay, global variable has no control. Okay, and this is the big picture of the inside the kernel. Every time you will have your own stack, so your own stack won't touch other people's stack, and that's why it will support parallel core of system call. Of course, if you want to look up your own information, it will look at your own task structure. Okay, so this inside the kernel what will going on, and here is the real picture of how memory is being used. Okay, I have a big thick thing here. It's correspond to this 2 to the power 30. Okay, so 2 to the power 30 range already reserved for this guy, and for the remaining, this is not just 2 bits, right? You know, it's not just multiplying that. It's supporting the user's memory. The user memory in the lecture, I give it a slice. I draw it as a big fat box. It's a pieces of pieces. Okay. Later on, we will talk about these pieces, not in Elite, but in a regular class, we'll also talk about these pieces. It's scattering around in the real system memory. Okay. So this is big picture, and I think do you need a break? Now is something routine that I will show you. You need a break. No, then I will talk about how to call a system call. This is a very, very interesting flow, okay? So let's say I want to call a system call, okay? And actually system call has a table that hard code is number. Because system call is just a array of function pointer, okay? And every pointer get a slot, index 0, index 1, index 2. And get PID so happen to be, let's say, 20 in a particular version of the kernel. Okay? So I know that it's a 20, so I will do the following. In a particular version, let's say in the version 2.6 of the kernel, then we will set up, because get PID don't have any parameter. Okay, so we don't talk about any parameter passing. We just talk about how to call that thing. You know, get PID don't have parameter, right? Yeah. So when I call it, I will load a number called 20 into a register called EAX. And in 64-bit CPU, it is not called EAX, it's called RAX. Yeah, something like that. Okay? Load that number in, and then immediately call this INTHTH. Okay? So this is just like storytelling. Now I can show you. I can show you. Now, have you downloaded the GNU-C library code? We will do the search now. Okay, I will fast forward to this page. Okay, let's check whether it is doing the same thing. Okay, if you have downloaded the code, go to this directory, the library source, system dependency directory, go to Unix, go to system 5. Okay, I don't know why it's put in system 5, and it's a Linux. I choose the old style 32-bit implementation. Okay, so let's do it. Okay, glibc, system dependency, Unix, system 5, Linux. Okay, I'm already there. So go to the 32-bit implementation. So many .c. Okay, what are the .c that you know? Seems nothing. A time, yeah, you know time. Okay. What is other? Oh, there's a vfog. Okay. So whenever you see .s, so what is .s? Assembly code. Okay, so include assembly code in the library. What are the things that you know? No, very few that you will know. This is the core of the malloc. Malloc will call the system call. Okay, so go back to the get PID. So what is the file name? The file name you cannot find it, right? So I just say that please look for the keyword enter kernel. So this is the first time that you use this tool. We call this grab. Okay. So we will try to grab all the files for this keyword called enter kernel. So this is the core inside a C library. When it want to go into the kernel, it will call this set of assembly code. Grab these pieces. Oh no, not C. Just all files. Okay. Are you in this directory? System dependency, Unix, system 5, Linux, i386, and grab the keyword called in the kernel. Okay? So it will skip all the directories, and you will find very interesting. There is a file called exit.s. Okay? Exit system call implementation. Cron, the backup call, a backup system for the fork. Okay? And so on and so forth. Now let's go to take a look at this. This looks sexy, right? It says there is a comment. Do the system call. Seems to be our target, right? So let's take a look at this so-called syscall.s. So I will use Atom to open it so that you can see some syntax highlighting. .s. And you can use let's use a vim, pickle, even gedit, text editor, whatever. Okay. So this is you can see this is GNU-C library. Okay, and so many codes here. And what are they? They're system call body. Okay, this entry syscall. Okay, so let's grab our thing. We want enter kernel. Enter kernel. So this is the enter kernel. It's called do system call, but this is not definition of the enter kernel, right? So this is one of the things that very very frequent that will happen while you are looking for code that you're interested. Sometimes you will only find the usage of something, but not the definitions. Okay, so don't get frustrated. We will do the search again. Okay, I want definition, right? Of course, I don't want to find the usage. I want definition. Where can you find definition? What is the particular keyword for C for a definition? Huh? Define. Right? You find define here. Okay? So that means that we failed the first search. How about here? Okay, so this is very typical. Even I always fail. Ah, it's not this. Okay, then take a look at another one. Take a look at another one. Okay, so let's take a look of and here I open it. .h. Okay, wow, and a big file. Huh? So let's search it. I found it. Okay, can you find the instruction that I just said? int. int is not defining an integer. Okay, int is simply called interrupt at this number. Okay, so this is the call to enter the kernel. Okay, in the GNU-C library. Okay, so if you really want to look for the truth, if you really want to look for the truth, this is just the beginning. That you understand that hey, actually GNU-C library when it want to go to the kernel, it will really use that int at call. Where will it use it? Okay, it's hard to say. Why? Because you have to do the following. If you want to do it, okay, you can ask me how. I don't want you, so I put so many spout here. Okay, so if you really want to look into the truth, I will ask you to decompile your GNU-C library. Decompile it. Okay, decompile and look for some keywords. Okay, you dump it out all the things, and then you will go to the last step to look for the get PID. I don't do it here. I don't want to KO all people here. Yeah. Dump it out and. What is the meaning? I decompile something real, and then I look for information. You can do it, okay? I don't know why. When I decompile it, I can still find some comments. Okay, very interesting thing. I don't do it. Just believe in me. Okay, it's go down using this guy, and inside the get PID implementation of the GNU-C library, it will really call this. Now inside the kernel. Inside kernel, what it will do after this int adh. Okay, so let's do some interesting thing. We will go to take a look at the real stuff. What is get PID implementation in the kernel? Okay, so where it is, you can do two things: either using your download source or go to the web. This is the web resource. Okay, you can browse through the kernel source tree here, or you go to your download source code, go to the sys directory, open the timer.c. Okay, so I will do the terminal side. So go back to my download source, and I will go to this version. I said that you will use 2.4.37, so I already download it. So if you didn't download it, okay, you can go to here, and go to sys. Okay, where's sys? I typed the wrong code. Oh, no, where is it? Kernel source sys. I missed one level. I should miss sys. Kernel sys, right? Nope. What? Sorry. I will use something. What is the file name? Timer.c. Fine. Timer.c. Sorry, I spelled rubbish. It's kernel, not sys. Okay, the kernel directory. So change this to modify it. Okay, to kernel. Okay. So in the web we can do the search. In here, the kernel directory. Go to the timer.c. Timer.c. Time.c. Okay, it's here. You find the code of get PID. Okay, so I will do it here. Go to the kernel, and we have so many .c here. I will open timer.c. All right, so this timer.c. I do a search, get PID. Okay, so this is the beginning of the get PID. Now this is the first time that you read kernel source code. Okay, so although it is a little bit dark, but this is the real implementation. Now give you some warning. The warning is kernel programmers seldom write comments. Okay, just like me, I never write comment. You are also, so you are qualified for being a kernel developer. Okay, whenever they put down comments, that means it is very important or something really hard to understand. So they write down things like this. Let's say, oh, it also say something interesting. I cannot show it here. How can I change the brightness? Brightness. Well, only change my brightness, not here. Okay. So let's do a search in the web then. Okay. Get very bright here. Get PID. Okay. So it's always said that the alpha is a CPU. Okay. Alpha CPU, you don't use get PID, it's get okay, it's telling you something important. And look at get PID call. That's it. Just return a variable. Yeah, return a variable. It's a current, so current. Current is mean the current process. Okay, the current process. There is a field called TGID. Okay, and then return, and this is get PID implementation. Huh? yeah. This is kernel code. Yeah, you give me a very good impression. Huh? Okay. Yeah, this is the get PID implementation. Don't look down on that. Okay. Take a look at the amount of comment here. So for me, because I always look at the kernel code, it means firewall. Yeah, it means very important thing. Yeah, so you don't need to know what is it. Okay, later on we will look into this structure. We call it structure task struct. The current is a task struct. Okay, and here is the get PID. Now we know that, okay, the get PID is so simple. Yeah, you call it and then I return it, but some other things you don't know, right? And assembly language, yeah, you don't need to know it. Okay, if you really want to dig deep into what is a get ASM language, yeah, there's a big tree here. You can take a look here to understand what is that. And when you look at the get PID call, you will find something like this. Before the get PID, there's SYS underscore. Okay, so usually this is just a simple name. This is name only. But for kernel programmer, we know that this means that the entry of a system call. Okay, this entry of system, they have other functions. Some functions in the kernel is very big, but without the SYS underscore. So that means this is only a function, but not a system call. Okay, and there are some bindings to bind the get PID call into this SYS underscore get PID. Okay, and it will return long. So you may ask, hey, why is this long but not int? Okay, because integer. Do you know what is integer, right? Size of integer or 32-bit CPU. How many bytes you have? 32-bit CPU. Size of integer. 2. I mean how many bytes? Okay, sorry, I mean bytes. Huh? Too much. 4 bytes. 64 bytes. 64-bit CPU. 4. Go to have a look now. Okay. 64-bit CPU, integer, 4 bytes. Okay, but long is your answer. Long is 8 on 64-bit CPU. Is 32-bit CPU is 4 bytes. Okay, so what is the meaning of putting in here? It means the return value will consume a word in the CPU. So what is a word? The basic processing units, okay? The memory look at it and transfer unit is always a word. And a word for 32-bit CPU is 4 byte, 1 long. For 64-bit, 8 byte, also 1 long. So it will choose the long data type to be the return value to just fit into the register size, the memory word size, so on and so forth. It won't use integer. Integer in 64-bit system is shorter. Okay, so later on when you try to add a system call in the next week, we will use a long data type as well. Okay, we won't use int. Don't use float. It is out of your expectation. Kernel don't have floating point implementation. No, don't add it. Okay, when you input a tuple into a float, you cannot compile a program. Not even compile a program. Okay, it don't know how to process floating point. Okay, in kernel. And this is a tradition. Whenever you get a success, you return 0. when you return bigger than 0, that means that your system call will return something extra. Let's say the get PID. It will tell the other side that, oh, the other side means the calling process. What is the number? So the number is not 0, not 1, not other things, but a long number. Okay? And usually, if you return -1 or smaller than 0, it means an error. Okay? So it is just a tradition. Of course, you can return anything as long as it's long. It's good. All right. So this is the system call, and I talk about the grab. Next time we will do some of the search. Okay. I give it as a homework. Okay. The homework is we have the grab, we have the find. The find is a search for a file. Let's say I want to find a fork implementation inside a kernel. You will do a find dot minus name and a fork.c. I give you a homework. Okay, I hope that next week or in a discussion, okay, you will find these two things. First thing, question 1. I treat in class. Maybe you are during the time that you're compiling the kernel. Okay, compile kernel sucks. Okay, take you 15 minutes. Okay, if your computer without power support, maybe 30 minutes. Okay, so you can do it in class or next time. Tell me the following. Yeah, 4日 what? 我4日唔得 oh, okay. The question 1 is something that I cannot teach yesterday. I should teach you one thing. There are a set of different signals. There is a signal called SIGQ. What is SIGQ? You may see some of your seniors or some of your friends type this. Q -9. Yeah, some process. Let's say the 1, 2, 3, 4. So what is -9? Yeah, you know -9. No, you know -9. Okay, the ultimate weapon, nuclear weapon, right? Always can successfully kill a process, no matter how stubborn it is. Okay, you can kill it. Okay, and a system called it SIGQ. Okay, and there is a process called init process. So where can you find init process in Linux? It is the PID number 1. It's PID number 1. So it is hard code. It's hard code in the system that, okay, even though SIGQ is a nuclear weapon, you cannot kill init. Yeah, and it is hard code inside the kernel. Okay, use the tools that I just introduced to you. The find call, the find where is it? The find, you can find a name. Okay, it will recursively start with the directory. I put a thought here. That means that the current directory. Start with here. Look for a name called fork.c. If you have multiple fork.c, it will tell you. Okay, my hint to look for this important init and the relationship between SIGQ and the init is actually hiding in the comment block. Is within the comment describe it, you cannot kill it. And the hint, the file name is signal.c. Yeah. Later, maybe you do the compilation or you go back home, do a search. Okay. Next time I will pick someone to answer me. Second is yesterday I remember who asked this question. You asked me these questions. Okay, and then I reply to you the repairing thing. What is the question that you asked? The zombie. Yeah. The zombie question. So when you ask me that, hey, how about there is a zombie and a parent cannot handle it, then I kill the parent, what will happen? Yeah, then you ask me the questions. Okay? And the question is, the answer is also in the kernel. Okay? The kernel will give you one thing. The operation is called reparent. Reparent operation. The reparent operation means that it will find a new parent, and the new parent is always PID1. Okay? It's always PID1. Give the init process always a grandmother, okay, of all the processes inside the process tree. And whenever your mother dies, you will be parent become a direct child of this PID. Look for that comment block again. So you don't need to know what is the C code. These two tasks is to look for comment blocks. Okay? And the comment blocks is to describe reparent operation. Okay? So here you don't have Google. You only have grab. You only have find. Okay? Or you can use this and click around. Okay? I don't recommend you to click around. Okay? Give you an example. I want to look for the name is called signal.c, right? Guess how many? So many, okay? So many signal.c. Hey, what happened? What happened? So, let me introduce to you this architecture directory. So, what is the ARCH? Is an architecture. Architecture directory contains so many subdirectory. Alpha, ARM. How many of you know ARM? Yeah, that ARM. ARM, how many of you know MIPS? No one knows? Yeah, I failed. Only one. Yeah, MIPS is still using CPU, okay? Some set-top box using MIPS CPU. What else? MIPS 64. PPC? No one knows PPC? PowerPC. PowerPC. Okay? So then you guess what's this? Oh, what is SH? I don't know. What is SH? Is this a shell? Okay. Yeah. This is what we call architecture implementation. The architecture has its own way to handle signal. So the signal thing about the SIGQ relationship between SIGQ and init kind of not related to any specific architecture, right? It should be something general. It should be something general. So you won't find that handling in PowerPC, but not in i386. i386 Intel CPU 32-bit implementation. You won't find it only in a specific area. So you will find it scattered everywhere? No. In kernel, we have an area to hold generic implementation. This is specific. Generic implementation is without ARCH. Here. This one is a generic implementation. So I give you a lot of hints. That means that you don't need to look at this bunch of things. This bunch is so many things. Oh, what are they? Okay. So this is architecture specific. Okay. So there are other directory that I can give you a very quick review over them. The quick review of directory, I skip it. Okay. We have so many architecture, driver. Okay, we have implementation of all drivers. You can find a keyboard driver. Okay, I try once. Okay, I try once, go to the keyboard driver, and whenever people type A, it becomes B. Yeah, this is doable. Yeah, because you're touching the driver, right? Or change all the mouse direction. Okay, up become down, left become right. Okay, guess how? Well, maybe you reverse the mouse, then you can use it. Okay. All the header files, file system. Oh, file system is sexy. Let's go to the file system directory. File system directory, where ls, the blue guys are the implementation of the specific file system implementation. How many names do you know for the blue guys? Where? Which one? Start with this column maybe. First, start with anyone know one of them? BFS. What is BFS? Not bad for search. Not bad for search. I know DFS.
Where is DFS? No.
Not BFS, not BFS. BEFS I know. It's from a BEOS. A BEOS is already gone. Okay. Here, second column, you may know more. USB? Where? Which one? Which one? Okay, here. FAT. How many of you know KernelFS? Oh, I am a little bit disappointed. KernelFS is one of the file system, read-only file system for embedded system. Okay, KernelFS. If you are from CE, you may have heard of, okay, but you don't know what it is. How many of you know this too? Yeah, you have seen this. Okay. This column I only know JFS. ISOFS I only know. HFS plus HFS, okay? Yeah. So this is a JFS I know. This is something special, not called FS, it's for journaling. Okay. Here, MS-DOS. Yeah, MS-DOS. And what else? And NFS is not NTFS, huh? Network file system. Okay. So you won't find other names that you may heard of but cannot find in here. Okay, you may heard of a particular file system. Can you find it here? Always can find it here. Okay, the upcoming file system, where are you? Oh, this is OFS, so O Linux. The coming file system is called ButterFS, BTRFS. Okay, ROMFS. Oh, this FS is kind of bad. Okay, so this riser is a man. Okay, so the name is called after the names of the inventor or the author. So now no one uses this file system. It's because of one reason, and the one reason is not technical. Okay, it's because this guy killed his wife. Okay, then people hate this file system. Yeah, I no longer use it anymore. So, but the implementation of this file system is very advanced, very forward looking. Okay, some of the things that I may have chance to talk about it. Okay, Samba is a Windows network file system. VFAT, also FAT. What is XFS? Right, I know that. Okay, so there are other .c. .c now is a generic implementation. We have pipe, we have OS, open system call is here. There's a read-write system call. Can you hear? Read-write.c. Super is not something super. Okay, later on we have a chance to talk about super. Okay, so this is all the core implementation, generic wise, hiding one place. Specific wise, it will move away, and the header files. This is interesting. The main function of the kernel is here. You can find the main functions here. IPC, inter-process communication, the kernel data structure all in here. is not 美美, okay? This is a memory management. Okay, it's memory management. Okay, so you can find all things here in the 4.0 series. We have more and more directory. Okay, I cannot take all of them already. Okay, so that's why I give you this. I give you the 2.4 to have a start. Others this is for the compilation, the script compilation, the network thing, library also for the compilation stuff. What else? Crypto, the encryption, the hash. MD5, SHA, architecture, I already tell you. Documentation is very interesting. They write a series of documentation over the kernel or in plain text. Yeah, take a look. Open Atom here. Let's find one thing. Let's say you're interested in floppy. Okay? The file describes the floppy driver. Describe floppy driver. Okay. Oh, it's still using Rhino. Okay, Rhino is a very old system bootloader. Okay. So, ThinkPad user, read this. Yeah, if you're using ThinkPad, read this. Okay. And all the documentation is here. How to control things. I seldom tell you to read it because it is for kernel developer to read. Okay. So today I will stop here, okay, because of when I talk about kernel development, I cannot stop, okay.